Okay, I think we can start. So the next lecture will be given by Professor Jessica Fintzen, and the title is, as written on the board, a category of representation of p-adic groups and Hecke algebras. Please.
Thank you very much. Oh, I'm on. Excellent. Thank you very much for the invitation to give this a talk at this wonderful conference in honor of Professor Tits. The last talk was about finite groups and buildings and the relation between these two, how the buildings had a lot of influence on finite groups. This talk will be about p-adic groups, and in this case, the affine buildings introduced by Bruhat and Tits will play an important role. So essentially, everything I've done builds up on work of Tits, in particular on the joint work of Bruhat and Tits. All right, so also feel free to ask questions anytime. Let me know if you can't see or can't hear. All right, and I hope I don't fall off the stage. So P is a prime number throughout this talk. And I said I want to not work with finite, but with p-adic groups. So F will be my p-adic field. By p-adic field, I mean either finite extension of the p-adic numbers, or I also allow that F is a, Laurent series over a finite field, so an equal characteristic non-Archimedean local field. So any non-Archimedean local field is allowed, and F contains a ring of integer O, which contains a uniformizer var pi, and the residue field is denoted by FQ if necessary. And then the main object will be denoted by G. G is what I call a p-adic group, so G is a connected reductive group over the field F. So for example, GLN, SLN, or the symplectic groups, or the orthogonal groups, the special orthogonal groups. But you can also think of crazy examples, like crazy forms of E8, whichever you like. I want to make one small assumption. So I want to assume that this group splits over a chainly ramified extension. Chainly ramified extension of the field F. So that means most things are fine, but I don't allow wild tori. So, for example, all the division algebras are fine. The units in division algebras, they all become isomorphic to GLN over a tame extension. So that's the setup. What do we want to do with it? What is the goal? The goal that I think mathematicians have been working towards for more than 50 years, and that got refined with time, is that we want to understand and explicitly describe the category of all the representations of the p-adic groups. So let me add some more adjectives of the category of all smooth, complex representations of G of F, my p-adic group. Complex means that I look at representations with complex coefficients, so map from our p-adic group to the space of automorphisms of a complex vector space, usually infinite dimensional. If you like, instead of complex numbers, you can also put FL bar here for L different from P, and the building blocks work the same. The category itself is more complicated, so what I'm saying does not hold for the category in the whole totality yet, unfortunately. Smooth means that the stabilizer of every vector contains an open subgroup, so that means every vector is fixed by some open subgroup. So that means a lot of the group is doing nothing, but still we get infinite dimensional representation, so we still get a rich and interesting category. Yeah, so that's it. That's what we want to do. We want to try to understand what this category is. And so how do we do this? So there are two steps to doing this. The first step is that we need to find building blocks. And so the building blocks are called supercuspidal representations. And why are these the building blocks and what is their definition, I'm answering both questions at once. So here's a nice fact, which says that if pi is an irreducible smooth, I will not say smooth all the time, but all my representations are smooth. If pi is an irreducible smooth representation of our p-adic group, then pi can actually be embedded into the parabolic induction from some parabolic subgroup, so from some Levi subgroup times the unipotent radical to the whole group of a representation sigma, where sigma is a supercuspidal representation of the Levi subgroup. So we extend trivially on the unipotent radical and then induce up. So every irreducible arises in the parabolic induction of a supercuspidal representation, and the supercuspidal representations are those that do not arise in a parabolic induction from a proper parabolic subgroup. So the supercuspidals are those where you have to choose m equals g. So that's the first fact. So that was actually known already more than 50 years ago, I think. And the difficult part was then to figure out what are these mysterious supercuspidal representations, and once we have them, how to get the rest out of it. And so how do we get everything out of it? So that's the so-called Bernstein decomposition thing from the 80s, which says we want to, okay, what do we want to do? We want to understand the whole category. So that's my category. That's this category here. I didn't. Oh, okay, I'm not a handball player. This is the category of smooth representation. We want to understand this category, and Bernstein tells us that this decomposes into a direct product of blocks. And these blocks are indexed by m and sigma, and these are really the building blocks. They can't be decomposed further. What is the indexing set? So the indexing set is consisting of pairs. M is a Levi subgroup like here, and sigma is a supercuspidal representation of n. So we know that every irreducible embeds into the parabolic induction of something, and we use that information to decompose our category. So that means this Bernstein block here, this is called a Bernstein block. And this Bernstein block contains all the irreducible subquotients. Well, I don't need to put irreducible there, because it's category, we take everything, not just irreducible. Sorry? It's hard to read? Good, then I'm not doing this in red. So now it's just hard to read that it's a Bernstein block, which is not a disaster. And the Bernstein block consists of all subquotients of the parabolic induction of this supercuspidal representation. So I induce this supercuspidal representation up to the whole group, and then check what's contained in there. And that's, maybe I shouldn't say consists, sorry. I meant contains. And that's contained in this block. But of course, I can also take any extensions that I can build out of that, because it's not just irreducible representations. So that means, what else do I need to tell you? I said they are indexed by these Levis up to pairs of Levi and supercuspidal up to equivalence. It doesn't really matter for this talk what the equivalence is, so I'm not writing it down, but just saying it in words. Two pairs are equivalent if you can do the following. They're equivalent if you can conjugate one to the other, because conjugation, I mean, it's expected that you get equivalent things. But you're also allowed to twist the sigma by an unramified character. An unramified character is a character that's trivial on compact subgroups. So that's something technical, but that doesn't really matter too much. The whole point is our category decomposes into blocks that are indexed by these Levis and supercuspidals. We'll see a supercuspidal a bit later in this talk. And they are just containing these elements, I mean, whatever you can parabolically induce, and everything that should also fit in the block. So everything where there are extensions that are non-trivial between them. So that's the Bernstein decomposition. So that has been known for a long time as well. And now what we need to do is, well, if we want to understand this category, well, we want to understand what each of these blocks are. So this result reduces the problem to studying each of these blocks individually. And so here's the vague theory, vague result that I want to talk about in this talk, and that I'm going to make precise as we go along. I just want to give you a small teaser of where we are going. And so this is actually in progress. It's not yet written up. And it's a joint project with Jeff Adler, Manish Mishra, and Kazuma Ohara. That's the main result that I'm writing down. But, well, since it's very vague, in order to get the input for small primes, there's also joint work with my postdoc, David Schween, that goes into this. So that will give us more input for small primes. This will become clear throughout the talk what I mean. So what is the result? The result is, and when I write this down, you might first wonder, what is that about? Because that's not really helpful. The result is that this block is equivalent to the same block where I just put a 0 everywhere. Now you might wonder, what's the point of it? I have to write more because I have to write zeros. The point of this is that, what is the sigma 0? The sigma 0 is the so-called depth 0 supercuspidal representation. And I will explain later what this means, but it means that this corresponds to representation of finite groups of Lie type. And the importance is that this block here is a block for depth 0 representation, and that means that this block here is rather well understood, and has been rather well understood already since the 90s. Well, we add a few details to it, but that's roughly the idea. So the idea is, the vague result is that every block is equivalent to some other block, and this other block is something well understood. And I will actually explain to you what I mean by well understood throughout the talk. The other thing of this result is that it says arbitrary representation theory can be reduced to depth 0 representation theory. And this will actually, I expect this to be a really helpful tool. If you want to prove something about arbitrary representations, you can try to prove it for depth 0 representations instead. And these are essentially representations of finite groups of Lie type. So we're translating a problem about p-adic groups to a problem about finite groups. And that has the potential to be very useful. So I expect there are a lot of applications within representation theory, but also when you want to construct, for example, local Langlands correspondence, I expect this to be very helpful. So for example, recently there has been a lot of hype about doing everything at a higher categorical level, in particular also to study categorical local Langlands correspondence, and it's current work in progress of others to write down a categorical local Langlands correspondence for depth 0 representations. And we know that on the Langlands parameter side, so the idea of the Langlands correspondence is to attach to a representation, or to the derived category of representation if you want to enhance everything, a Langlands parameter, or sheaves on the stack of Langlands parameters. And so if you can do this for the depth 0 part, the idea is then you can use this result to reduce everything for arbitrary depth to the depth 0 setting, and thereby also obtain, for example, a categorical Langlands correspondence in full generality. So that will require more work, but that's one expected application. Sorry, that's just a bit of hand-waving why you should be excited, even though this looks rather boring. All right, so that's the goal. That's where we are heading to. Let me see. I don't see anyone raising their hand for questions. Yeah. Yes, it doesn't depend on the parabolic. I mean, so what you really can do if you want to construct all the irreducibles in here, you can take all the all possible parabolics containing all the m's and the sigma and induced, but also all the equivalent pairs. So I said up to equivalence, so you can take anything in the equivalence class and then take the sub-representations of it. That would be one way to get all the irreducibles. Maybe I don't understand the question.
I think that when you change the parabolic containing m, the induced representation will be, so you had an equivalence relation just in the pair m sigma and not in the pair m triple m parabolic sigma.
Correct.
And this implicitly, this means that it depends, RGM sigma depends only on m sigma and not on the parabolic.
Correct.
But this requires to normalize the induction. In other words, to use something like unitary induction.
So I'm asked, shouldn't I normalize the induction? But if I'm too close to the blackboard to be sure about everything. But so usually, often what you do is you normalize the induction by some factor that ensures that it preserves unitarity. But this normalization factor is, I think, actually trivial in compact subgroups. It's an unramified character. So that means I could twist sigma already by it and not lose anything. So I can twist sigma here by any unramified character I want.
Because of this convention of the unramified, okay.
Exactly. So this equivalence here means I'm allowed to twist sigma by any unramified character, in particular by the character I need to twist it by, which is usually denoted by delta 1/2, square root of delta, that makes this unitary. Yeah. So I haven't actually told you which induction I use, whichever you like, the normalized or not. Yeah, excellent question. For those who didn't know what we were talking about, it doesn't matter. I try to just simplify things, and that's not a problem. So let's try to understand this block. So what's my talk going to be about? My talk in the first quarter was that. The second quarter, I will tell you a bit how one can understand these blocks. I will give you some examples. And then in the last quarter, I will tell you where are we at, what are the results, and make this wake theory much more precise. All right, so how do we study these blocks? We study them using type theory. And so what is a type? A type is a pair consisting of a... Oh, let me actually, before I write that down, let me give you an example, because when I'm sitting in the audience, I always want to see examples. So let me give you some examples. Let's say G is the group SA2. What are the possible interesting things? So the first case, what can we choose as Levi subgroups? There are many choices. The Levi subgroup could be either M is equal to G or M is a torus. If M is equal to G, then sigma is just a supercuspidal representation of G itself, so of M of F, which is equal to G of F. And we induce this to itself so nothing happens. So that means, what is this block consisting? Oh, now I wrote rep instead of R. Should be more consisting. What is the block corresponding to G and sigma? Well, the only irreducible representation in here is sigma. It's the thing that's contained in the parabolic induction from M to G. And there are just no interesting extensions of sigma with itself, because sigma is supercuspidal. It's a nice fact. So that means the only thing we can really have as objects in this block are just sums of sigma, arbitrary sums of sigma, arbitrary direct sums. And that's it. And then the endomorphisms are just, well, on sigma, it's just multiplying by a constant. So there's nothing really interesting. So this block, the supercuspidal block, is rather boring. Well, you might want to ask what sigma is, and I'll tell you in a bit. The second case is the case that that M is T is just so the diagonal matrices inside SA2. That's the other option that we can have. And then let's say I take sigma just for fun, the trivial representation, then the corresponding block corresponding to T and sigma. So I should say the torus doesn't have any interesting Levi subgroups. Therefore, every representation is supercuspidal because nothing arises from parabolic induction from a smaller one, in particular the trivial one. And so then if I take the trivial representation here, this block, well, this is called the principal block. And what is contained in the principal block? So how do we build the principal block? Well, we induce up from the parabolic containing T, so let's say a Borel, which is just, say, upper triangular matrices to the whole group, G. We induce up the trivial representation, and then one can check that this contains the trivial representation. So that means, in particular, the trivial representation is contained in this block. But the quotient here is non-trivial, and is called Steinberg. So also the Steinberg representation is contained in this block because this is actually a non-trivial extension, it's a non-split extension. And so you see here, this block was rather easy, it's just direct sums, while here we already see there are two different elements and some non-trivial extension. So this block here is actually much more complicated to describe. We see two objects in there and something non-trivial happening. And so the goal of the talk is to understand these better. So how do we understand these blocks better? We do this using type theory. So here's the definition. A pair K, rho consisting of K being a compact open subgroup of our p-adic group. Okay, I'm not tall enough. And rho being an irreducible representation of K. Such a pair is called an M sigma type. So it's a type for a Bernstein block with index M sigma if for all irreducible representations pi of the group G of F, the following are equivalent. So the following two statements are equivalent. The first statement is that this representation pi is contained in the Bernstein block attached to M and sigma. And the second statement is that if I take my representation pi and restrict it to this compact open subgroup K, then it should contain rho. Or in other words, we can say that the space of K homomorphisms between rho and pi is non-trivial. So let's digest this definition. So an M sigma type is a pair consisting of a compact subgroup and the representation of it that detects whether representations lie in the Bernstein block or not. By doing the following, it says the following is equivalent, the representation lies in the Bernstein block, if and only if this representation restricted to the compact subgroup contains our irreducible representation rho. So types are a way to detect Bernstein blocks via compact subgroups. And now you can smell Tits already, because the idea of Bruhat Tits was to find a way to parameterize large compact open subgroups. So that's our goal. We want to understand the category of representations of p-adic groups. So let me give you some examples. Let me give you depth 0 examples. Depth 0 types. I need a letter. All right. Let's do the example that G is SL2 that I've just done there. And let's work out types for these blocks over there. So the first case, the case where M is equal to G, I want to give you an example of a type. As my compact open subgroup K, I take SL2 over the ring of integers O. And now I need to give you a representation rho. What do I do with my K? I quotient out this subgroup consisting of the matrices of 1 plus var pi, the uniformizer on the diagonal, and var pi, the var pi is the uniformizer. 1 plus the uniformizer times O on the diagonal uniformizer times O off diagonal. Well, determinant equals 1 whenever I write this. So in other words, I quotient out all the matrices congruent 1 modulo the uniformizer. So this is just isomorphic to SL2 over the residue field. Now I need more space. All right. And now, here's my finite group. Excellent. A lot of people like finite groups. Now I just compose this with a cuspidal representation. So representation that doesn't come from parabolic induction, proper parabolic induction of this finite group to, well, its space, wherever it lives. And so this whole composition, I call this rho as well. And then k comma rho is a type. And it's actually a type for what is the pair? Well, M is equal to G, and the representation is the compact induction from K to G of this representation rho. So it turns out that this compact induction here is actually an irreducible supercuspidal representation. So compact induction means I take all the functions that transform on the left on K via rho, and that are compactly supported, and that gives us a supercuspidal representation. And this pair K rho is a type for it. So something lies in this Bernstein block, so it's the sum of this. Well, since it's irreducible, is exactly this, if and only if a representation restricted to K contains rho. All right, first example was this. Second example is our torus. In that case, so M was our T, sorry. So M, the Levi, is our torus. In that case, as K, I like to take the Iwahori subgroup, so matrices of the form O, 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 var pi O. And as representation, I take the trivial representation, and this is a type for the case of the torus together with the trivial representation. So if you want to figure out if something lies in this complicated block here, this principal block, all you need to do is you restrict to the Iwahori subgroup and check if it contains a trivial representation or not. All right, that was the case of SL2. Now I want to, since I promised you to talk about depth zero types, I want to do the general case. Sorry, people in this corner might have to move to the other side, as I told you. So the general case, for simplicity, let me just assume that G is semi-simple and simply connected. I can do it in full generality if you like, but to just simplify notation, I'll do it in that case. In this case, so these were just some examples of depth zero types, but they are almost all. So what are the depth zero types in general? In general, as my K, as the K, I take something that is called G sub X, which is the stabilizer in the group, in the p-adic group of the point X. And what is X? Well, X is a point in the Bruhat-Tits building. So the Bruhat-Tits building is an affine building that classifies rather large compact subgroups. And the group acts on this affine building, and I like to take a stabilizer of a point, so that's a compact subgroup. All the maximal compact subgroups arise in this way, but there are also some smaller ones like the Iwahori. So in the case of, don't worry, if you're not fluent with Bruhat-Tits building, so that's not necessary for the rest of the talk, but if you are, here you can enjoy that. In the case of SL2, what are all the possible options? It would be just conjugates of the Iwahori, conjugates of SL2O, and then conjugates of the matrices of the shape O, O, var pi inverse O, which are not conjugate in SL2 to SL2 of O. So these are all the options of these large compact open subgroups, and then we have to take a representation of that, and the representation, can people still see the last line here? Can you see the last line? No? Okay. So then the representation that we build is, we start with our K equals Gx, and then we mod out the pro-p unipotent radical, which is also called gx0 plus. So that's the pro-p unipotent radical. And this group here, so for example, this would be the pro-p unipotent radical in that case. This group are the FQ points of a reductive group. And here you have your finite group, so you just do the same as over here. You compose it with a cuspidal representation to whatever the space of its endomorph, whatever this vector space is. And so that's the whole composition is your rho. And so then this k comma rho is a depth 0 type. And that's how all the depth 0 types look like. So depth 0 type means compact open subgroup that you quotient by the as large subgroup as makes sense somehow. So the depth, well, let's say that you quotient by the pro-p unipotent radical. So by the depth 0 plus subgroup, and then you obtain a finite group of Lie type, and you compose that. That's a depth 0. Yes? What is the definition of depth 0? That is the definition of depth 0. And that's the definition of a depth 0 type. Yeah. More general, the idea is then try to skip that for that talk, but since you asked. So in general, I said I talk about smooth representations. If you have an irreducible representation, that means every vector is fixed by some open subgroup. But this subgroup might be huge or small. You don't know how large it is. And so what Moy and Bruhat did is they defined the filtration of this subgroup Gx by smaller and smaller compact open subgroup. And the depth of a representation is the question of how far do you have to go down in this filtration until you get fixed vectors. And depth 0 means you have already fixed vectors under just this 0 plus fixed group. And depth 100 would be that you only have fixed vector under the 100 plus filtration subgroup. So that's the depth. So that means the depth 0 ones are the ones that are the easiest, that are corresponding to finite groups of Lie type. And all the other ones would be that I quotient out a much smaller group. You have a much more complicated thing here to work with. Yeah. You could think of it as fixing larger and larger balls on the building. It's almost correct. Yeah.
Am I understanding correctly that every one of the keys that appear in the type are parahoric subgroups?
No, the question was if all the Ks in types are parahoric subgroups. No, they are not. For this particular case of depth 0 types for G being semi-simple, simply connected, yes. In general, K can be smaller and much more complicated. You can always induce up if you want to a maximal subgroup, but naturally they are smaller usually. But you could if you wanted to artificially enlarge. More questions? All right, so these are types. Types are, well, they are fun by themselves because they help us to understand these blocks, but they help us much more than you can see. So here is how they help us even more. So that's a result of Bushnell and Kutzko from 1998. They introduced these notions of types. And they said, so suppose that K rho is a type. K rho is an M sigma type. Then the really nice thing happens. Then this Bernstein block attached to M and sigma that we try to understand is actually equivalent to modules over a Hecke algebra that's attached to K and rho. Sometimes I might also write it as G, K, rho if I want to indicate the group. So the claim is, and I say in a moment what this is, that the Bernstein block is equivalent to right unital modules over this Hecke algebra. And what is this Hecke algebra? This H of K, rho is by definition, these are all the functions from the group to the space of endomorphisms of our representation V rho of the type, such that f of K, G, K prime is equal to rho of K, f of G, rho of K prime. So in other words, K pulls out on both sides. So I'm just writing down the obvious things that K and K prime are in K and G and G. the case pull out on both sides via this representation rho. It makes sense to pre- and post-compose endomorphisms of the space. And we also ask that F is compactly supported. So that's what the Hecke algebra is. It's just functions on G that transform on both sides according to rho. It becomes an algebra structure via convolution, something you can write down very explicitly. Or another way to say is this is equivalent to the space of endomorphisms of the compact induction from K to G of rho, depending on which viewpoint you like more. And then you just have composition. So that means we can understand the Bernstein blocks using these Hecke algebras, if only we understood the Hecke algebras. And maybe quickly, the Hecke algebra in this example here would be just C, it would be trivial, just one-dimensional, because the compact, yeah, I can say more, but let me not say more. And in this case, it would be an affine Hecke algebra corresponding to the Iwahori-Hecke, it's the Iwahori-Hecke algebra, so it's just an affine Hecke algebra. I can write this down in more detail if you like later. All right. So that's the theorem. So now what do? We want to understand these Bernstein blocks. So what to do next? What to do? What to do is a stupid thing to write. Let's write questions. Questions or tasks. Questions. What are the two questions that now come to our mind when we see this? Well, question one is, the statement starts with, suppose K rho is an M sigma type. Well, do these exist? So question one is, do types exist? Exist. Or rather, when do types exist? I'm sorry to the person who has to buy new chalk. And so that would be great. If we know types exist, we can apply this theorem. But then we have this equivalence. It doesn't help us if we don't understand the Hecke algebra. So what is the Hecke algebra corresponding to the type? So if we can answer these two questions, if we can answer if we know that types exist, and then if we can understand these Hecke algebras, then we can understand the blocks. And so that will be the last third of this talk, to answer these two questions. So here we go, answers. Yes, type exists, otherwise I wouldn't give this talk. Some examples are already there. So types exist for a lot of cases. So they exist for GLN. So actually, like the first thing people started to study before types was to just build these supercuspidal representations, just these sigmas, these indexing set. And that's what people started first for the group GLN already 50 years ago with work of Howe and Moy and others. And then that was finished by Bushner and Kutzko, who then realized this type theory as well. So they actually constructed all types for GLN. So there we have a complete story. That was done maybe 30 years ago. In some sense, even before they defined the notion. Then we also know it in the case of classical groups. So if we work with fixed points of an involution, so we take GLN, take an order 2 involution, and take the fixed points. So we get orthogonal unitary symplectic groups. Then if P is not equal to 2, we also know how to construct types. And that was done by Miucci and Stevens based on Stevens' earlier work. And then we also know it for inner forms of GLN that was done by Sécher and Stevens. And that's essentially the classical world. So let me keep the time. Now the idea is, what I'm interested in, what a lot of people are interested in, is to go beyond the classical case. So this work over there uses really GLN. GLN is an n by n in vertical matrices acting on an n-dimensional vector space. And you use this heavily here. And also for the classical groups, you embed them in GLN and make everything behave nicely under the involution. And the same for inner forms. If you want to understand all groups, well, then you have to call Tits. And together with Bruhat, they then introduced the Bruhat-Tits theory that allows us to study much more general groups. So for general G, the picture looks as follows. So after Bruhat and Tits introduced their theory about the building, then Moy and Prasad defined this filtration of these subgroups, of these big subgroups, and defined also the notion of depth over there. And what they did is they studied depth zero representation. I want to draw a picture about what we know and what we don't know. So I want to draw the depths down here. So that's depth zero. Depth zero is up here. And then we go down deeper depths. And so in this direction, I want to draw the prime number p because some results depend on the prime number p. And so what Moy and Prasad did, Moy and Prasad studied these depth zero representations. So these representations and the corresponding types were studied in the 90s by Moy and Prasad. Well, the notion of type was introduced a bit later, but they had a precursor of it, and from their work follows that. And I should also say Morris, who did independent work around the same time. And then people tried to get deeper down in this picture and try to construct representations of higher depths and eventual types. And so let me draw them as circles. And so who did this? So Jeff Adler, around shortly before 2000, constructed some supercuspidal representations. Then JKU generalized his construction vastly, so he constructed a lot more representations. And then Julie Kim, together with JKU, they observed that the same construction that JKU actually provided doesn't just provide us supercuspidal representations, but also types, which is what we are looking for. Maybe I should put my initial there for fixing a few holes in there. So here are all these types, which are circles. So these circles all represent some k and some rho. Now the question is, we want somehow all types. If we want to understand all Bernstein blocks, we need types for every single Bernstein block. And so that was then a big breakthrough. But if we are in the region where p is very large, then I think around 2007, Julie Kim showed that we actually, under the assumption that the characteristic of the field is equal to 0, Julie Kim showed that we get all the supercuspidal representations, and in the joint work with JKU, where they extended use work to types, they also showed that all the types arise in this way. And then in 2001, I actually showed, well, you don't need to go to the very large region. It suffices to assume that P doesn't divide the order of the Weil group, which for GLN means n factorial. For classical groups, usually around n factorial, you exclude all the primes up to n. For exceptional groups, in the worst case, you exclude 2, 3, 5, 7, not too much. And then you have exhaustion. So you get all possible types from use construction. So that's what I did. And I also erased this condition here. So that's now the picture. So the answer to the first question, do we have types, is yes. We have types under the assumption that P doesn't divide the order of the Weil group. Under this assumption, we can really say, let K rho be a type for M sigma. So they exist in this case. Now I need to, unfortunately, erase. So. Can you, for an M sigma, have different types? This is an excellent question. Yes, you can. I mean, first of all, you need to define what does different. So there have been people studying uniqueness of types, where they define an appropriate equivalence relation. And then the answer was, there was Peshkuna's thesis that for GLN, the types are unique. But in general, I was just told by, I think, Naoki Imai, that a student of his has a counterexample, I think, for GLN over division algebra. So types are not unique in general, but in a lot of cases. And that's actually, it's a good but very difficult question to understand uniqueness of types. And all these questions here are really studied using the Bruhat-Tits building. So even though you're not seeing it so much in the talk, because I'm not telling you all the details of all the proofs, Bruhat-Tits theory is really underlying all these things. All right. I was promised 3 colors. I haven't used yellow yet. So here comes yellow. So there are actually a bunch of dots missing in this region. And some small dots have been added already through work of Reader and you, together with work of myself and Beth Romano and just myself. And what I'm currently working on, so that's an expected result. It's not yet written up, so I call it expected, and there are a lot of things still in progress. So this is in progress, together with my postdoc David Schween, which is actually to construct more types for small primes. So we provide a construction of some, and in some sense, every tame of some new tame types for small p. So for small p, it's not exhaustive yet. More has to be done. And we are currently working on providing a new construction of really genuine new types, but types that are still considered tame. And all right, that's what we are working on. And the last 5 minutes, I wanted to actually now answer question 2. So that's the answer to question 1. So essentially, types exist. Up to some small details, work in progress. And so then the last question is, what are these Hecke algebras? And that should also get back to the rake result that I promised earlier. And so here's the theorem about the answer to the second question. That's also in progress. It's in progress, but further in progress. So the draft already has 130 pages for that one. And that's a joint project with Jeff Adler, Manish Mishra, and Kazuma Ohara. And that says that we do understand the Hecke algebras and relate them to depth 0. So here's the precise statement. Let K rho be a Kim-U type for M sigma. Let me just write it for M sigma here. So an M sigma type. So M is a Levi sigma supercuspidal, and K rho is a type. So that means any of these red types is what we consider. We actually consider a much larger class, so it should also apply to these yellow dots here. But in particular, it applies to everything in this red region. So if we have such a type, then the theorem is that there exists the following. There exists a subgroup of G. It's actually a subgroup that becomes a Levi subgroup over some tame extension. What else does exist? There exists a Levi inside G0, and there exists sigma 0, depth 0, supercuspidal representation of this Levi subgroup. And finally, there exists a type for this. And there exists K0, rho 0, and M0, sigma 0 type. Such that the following happens, such that the Hecke algebra attached to K and rho, the one that corresponds to the Bernstein block of M sigma, is isomorphic as an algebra to the Hecke algebra corresponding to the smaller group with the depth 0 type. And we understand that. Let me use maybe a new blackboard to not get too, sorry, not new blackboard, new section of the blackboard to not get too low. And this is actually something that we understand. So let me just call this a new theorem. And let me attribute this to Morris from the 90s already. Let me maybe say, in parentheses, our initials to actually enhance the statement to the statement that it's here. So Morris only studied a union of Bernstein blocks rather than a single one, but let's not worry about the details. So what Morris said is that he actually understands this Hecke algebra very explicitly. So he gives explicit generators and relations, and a short way to write it is, this is actually a semi-direct product of some twisted group algebra, some group algebra attached to the sigma 0 with some cocycle, semi-direct product with an affine Hecke algebra attached to some affine Wahl group that's attached to this sigma 0. It's not the affine Wahl group of the group, it's just some affine Wahl group together with some quadratic relations. So once more, what does Morris say? Morris gives explicit generators and relations for the Hecke algebras that written in one formula says the Hecke algebra is actually an affine Hecke algebra, something a lot of people love and understand. Semi-direct product with just a group algebra, just with some small twist there. I'm happy to write down formulas for affine Hecke algebras if people like to afterwards, but just for now, all I really want to say is this part we understand, and now we relate everything back to that, so that means we really understand all these Hecke algebras. I have 0 minutes left, but I think I owe people to not stop here before saying who actually proved things before. So let me use my half a minute that I don't have to say the same result. This result was proven earlier in the case of by Roche in 1998 in the case that M is equal to T is a maximal split torus, a split maximal torus. So in particular, the group is split and was proven by O'Hara in 2021 in the case that M is G, so the other extreme that we are in the supercuspidal case. And has been proven also for small examples or also in the case of the general linear group earlier. So classical groups are fine, small examples are fine. But in general, apart from these two extreme cases, this is the first time that we actually get that result. Okay, thank you for sticking for another minute with me.